come back to these lectures on linear algebra. Let me recapitulate what we did in the last lecture. Let K be a field. On the set of polynomials Kx that we are denoting this is a set of polynomials with coefficients in K we have defined operations addition of polynomials, multiplication of polynomials and also scalar multiplication of K on the polynomials Kx. And note that we have mentioned that I mentioned that these operations are compatible with each other. Especially I want to note the scalar multiplication and multiplication of a polynomial. So, that means how the compatibility of these two operations means given two scalars a b and two polynomials f comma g in Kx, whether you multiply first a scalar and a polynomial af and b times g. So, you get polynomials and now you multiply these two polynomials. On the other hand, you first multiply the scalars and then multiply this scalar to the polynomial product polynomial. So, this operation should be same, this result should be same, that is the compatibility of scalar multiplication of k on the Kx and the multiplication of polynomials. So, such a total structure, this structure Kx with this structure is called a K algebra. Or algebra over K. Note that this means you have to separate two things together, that is Kx with plus and multiplication of polynomials. This is a commutative ring and Kx with addition of polynomials and the scalar multiplication. It is a K vector space. And these two structures are compatible, and the compatibility just means the scalar multiplication is compatible with plus and scalar multiplication is also compatibility with the multiplication of polynomials, and this addition in this vector space and addition in this ring are same. So, all these together is encoded in one word saying that it is a K algebra. Okay. So, further I will also discuss about prime polynomials, prime polynomials are in Kx are the polynomials, these are irreducible polynomials Irreducible polynomials are by definition they are non-constant polynomials, that is degree of p is bigger or equal to 1 and p cannot be decomposed as product of two non-constant polynomials f g, both non-constant, with degree f bigger or equal to 1 and degree g also bigger or equal to 1. You cannot decompose these into the product, and in addition to that p is monic. P is monic means that is the leading coefficient of p is 1. These polynomials are called, such polynomials are called prime polynomials, and they have the same rule like prime numbers. And understanding the prime polynomials over an arbitrary field is a complicated problem. However, one can describe them for special fields like complex numbers, real numbers, etc. But I will continue a little bit more. So, the important, so this algebra Kx, this ring, the ring, this is similar, exactly similar to that of ring of integers. So, we have seen the analogues of prime numbers or prime polynomials, also division with remainder, also Euclidean algorithm, and so on. So, in addition to that, I also would like to note this theorem on, this is a theorem on uniqueness of prime decomposition. Such a theorem, we know such a theorem holds for integers, and that theorem was called fundamental theorem of arithmetic. In this case, this is the analog of fundamental theorem of arithmetic. So, it has the existence part and uniqueness part. So, existence part is simple, that any, even uniqueness part is simple. So, this theorem says that every non-zero polynomial f in Kx can be decomposed uniquely. So, when one says uniquely, that means up to an order. Decompose uniquely into product of prime polynomials. In the notation, if f is non-zero polynomial in Kx, then you can write f as some constant times p1 n1 pr nr, where p1 to pr are distinct prime polynomials and n1 to nr are non-zero natural numbers. They are called the multiplicities of those prime factors. So, this is the same analog of the fundamental theorem of arithmetic to this ring. This will be used quite often later in some some discussion. Now, first I should give some examples. So, for example, no, I need couple of definitions. So, first let me give couple of definitions. So, this is zeros of polynomials. Also one can call them as solutions of polynomials. So, like we have seen in earlier lecture linear polynomial solution space, like that now we are considering arbitrary polynomial, but only one variable. So, let f(x) be a polynomial with coefficients in the field k and alpha be an element in k. We say that alpha is a 0 of f, or some people say or alpha is a root of. If when you substitute x equal to alpha, f of alpha, this should become 0. So, I would therefore like to stick to this 0 of this terminology rather than the root. This is equivalent to saying f can be written as a product of the linear factor x minus alpha times some q, where q is some polynomial, and obviously the degree of q will be exactly 1 less than the degree of f. This equivalence follows immediately from the division with remainder. So, this is for this one needs to use division with remainder. So, polynomial with coefficients in k may have 0 in k or may not have. For example, the polynomial x square plus 1 with real coefficients, if you think them as real coefficients, then this polynomial has no 0 in real numbers. Whereas, if you take this polynomial x square minus 2 in real numbers has exactly 2 zeros in R, namely plus root 2 and minus root 2. Whereas, the same polynomial, if you think is a polynomial with rational coefficients, then has no zeros in Q, because the zeros are precisely plus minus root 2 and they are not rational numbers, because since plus minus root 2 they are not rational numbers. So, therefore, when one talks about your roots etc., one needs to specify the field more carefully. Also, I will introduce a notation here that V k of f, this is all those alpha in k such that alpha is a 0 of f. This is a finite subset of Q. It could be empty also. This is called the 0 set of f in K. For example, in this case, if you take this as rational numbers, it is an empty set. If you take over real numbers it is plus minus root 2, this has empty set and so on. One more example for finite field. Now, suppose you take k equal to z mod p and the polynomial x power p minus x, then you know that all elements if alpha is in k, remember k is z mod p, and you know that alpha power p equal to p for all alpha, because the group zp cross the multiplicative group of that finite field z mod p is cyclic of order p minus 1, and so alpha power p minus 1 is always 1 and you multiply that by alpha. So, that means this means the zero set of in z mod p, zero set of the polynomial x power p minus x is all z mod p. All right. You can also do little bit finer analysis, that if you have a polynomial you can try to take out all the possible zeros as a product, because we have seen if alpha is a 0 then x minus alpha is a factor. So, every polynomial f, therefore, we can write it as a times x minus alpha 1 power n1, x minus alpha 2 power n2 and so on till x minus alpha r power nr. Still some polynomial part may be left who do not have 0 at all. So, that is g with first a is in scalar, a is a scalar, alpha 1 to alpha r are elements in k distinct, n1 to nr are the multiplicities of alpha 1 to alpha r respectively and they are non-zero natural numbers, and g is a polynomial with coefficients in k with the property that with g has no 0 in k. It may happen g could be prime or may not be prime. If it is not prime, further you can decompose into the prime factors, but those prime factors will also not have any zeros in the field k. So, in any case we can also write this as this product as it is, and then further write g as a product of prime polynomial. This is m1 ps ms, where p1 to ps are distinct prime polynomials and m1 to ms are their multiplicities in f, and pi none of the pi's have any 0 in k. For example, just one could write easy example. One could write an example like this. If you look at x minus alpha, x minus let us say 2 power 1, x minus 3 square, x minus 5, then x square plus 1, x square plus 2, this is, think of this is a polynomial with real coefficients. These guys are corresponding to the zeros 2, 3, 5. The multiplicity of the 0, 2 is 1, multiplicity of the 0, 3 is 5, multiplicity of 5 is 1. These are prime factors, because these polynomials cannot be further decomposed into to linear ones, because minus 1 does not have square root in real numbers, negative numbers have no square root. Therefore, this, and you can cook up any example with any configuration. All right. So, in general we could also write the degree and f. So, degree of f in any case will be bigger equal to the sum n1 plus n2 plus nr, and the cardinality of the 0 set of f will be bounded by the number r. So, these are, because we are counting, when you count in the set 0 is counted only once, but in this product, so this formula is finer, this is finer than this inequality. Further, if your field is better, field has nice properties. Further, if one takes k equal to r, then you can of course improve the things. Then we can, there is no, the other part does not exist, then I recall what is called as fundamental theorem of algebra. This was first time stated with D'Alembert, the French mathematician D'Alembert. He stated this formally in 1746, and the first correct proof is due to Gauss in 1899. That was his PhD thesis. It says that let f be a polynomial with the complex coefficients, then f can be, then f has a complex 0. That means there exists a complex number z in f with f of z is 0. And when I say polynomial, non-constant, so that is degree f is bigger equal to 0 or bigger equal to 1. So, once you do this, then x minus z will be factor of f, and then the remaining part again you can apply this theorem. So, in particular we will get a decomposition like this, f equal to some constant x minus z1 power n1 x minus zr power nr, where z1 to zr are different distinct complex numbers and n1 to nr are the multiplicities of these zeros, they are non-zero natural numbers. So, in this case V C of f is precisely z1 to zr, and if you count them properly, then you get a nice formula, that is degree f equal to n1 plus n2 plus nr. Otherwise, you adjust less equal to. So, this theorem will be often used especially in the computation of eigenvalues, characteristic polynomials, etc., and normally in courses like linear algebra one does not prove this, but assumes this. So, I am also going to assume this theorem. Okay. All right. So, coming back to our vector spaces, this was a little bit long digression with polynomials etc., and I will come back to it with a more force in rational functions, but I will not talk that now. So, this was a point to give an example of a vector space and a basis generating set, linear independence, basis etc. So, this vector space Kx, we have noted this Kx is a K vector space. Obviously, I will keep noting A, B, C, A. If you look at the family 1, x, x square, all powers of the indeterminate and so on. This is a generating system. For Kx. This is obvious because we know any polynomial is a linear combination of these powers of x. So, but note that this family is not finite, it is a countable family, but it is not a finite. B, want to say that this family 1 x, x square etc., x power n etc. is also linearly independent. Over K. This is again obvious because if you have a finite sum like this a0 plus a1x plus an power xn, if this is 0, that means this is a left hand side is a polynomial which is a 0 polynomial, but that means by definition all these coefficients are 0. This is the definition of a polynomial. So, putting together we know that 1 x, x square etc., this is a basis, this is a K basis of Kx. So, Kx needs infinite basis, countable basis. So, later on when I introduce a concept of dimension, we will check that the dimension of the vector space Kx is countable, but this I do it in the next section. But now the next example I want to, so I forgot the number, let me check the number. This was a rather long discussion on the polynomials. I thought it is a good idea to recall about polynomials. Okay, so fourth example. Okay, so this is example 4. Now, this is I want to discuss polynomial functions. So, see, note that each polynomial, every polynomial f with coefficients in the field k, you can think of a function, can be thought as a function from where to where, from k to k, and that also I keep denoting by f only. But remember, when one says, one has to be little careful when writing what you are talking. So, which function? Any constant, just substitute that constant instead of a variable f of a. So, if f were a0 plus a1x etc. an xn, then f of a is just putting capital X equal to small a0 plus a1a plus a2a square and so on, an a power n. This makes sense, and it is an element in K again because all coefficients were in K and we started also in A in K. So, it is a function from K to K. So, every function from K to K of the form any, now let me use t because t is varying in K. T goes to a0 plus a1t plus an t power n with a0 to an are in K. Such a function is called a polynomial function, is called a polynomial function. And note that this is an element in K power K in our notation. I will end this first half of the lecture with the following example. This is just to show you that these coefficients may not be uniquely determined. So, for example, if you take the field to be K to be equal to Z mod P and upon the two functions K to K, any A goes to 0. This is a constant function. On the other hand, take the other function K to K, any t goes to t power p minus t, and we have just seen above that every element of K t power p equal to t. So, this is indeed a 0 function. So, these two functions are equal. So, in this case the coefficients were minus a0 and the next one is ap, which is 1. So, in this case a0 equal to minus 1 and ap equal to 1, and in this case all coefficients are 0, both are 0 functions. So, this is a different representation than this. So, this, unlike polynomials, the coefficients are not uniquely determined. Okay. Thank you. So, we will continue after a break.